Welcome to aminacademy.com. In physics, let us discuss about fundamental and harmonic frequencies. The lowest possible frequency at which the string would vibrate to form a standing wave pattern is known as the fundamental frequency or first harmonic. The second lowest frequency at which the string could vibrate is known as the second harmonic. The third lowest frequency is known as the third harmonic, and so on. Look at the figure. Here, this is the fundamental frequencies. This complete one set. Here, first overtune, that second harmonic, like it comes, is a third harmonic, fourth harmonic. For the detail, fundamental and harmonic frequencies. Musical sound consists of fundamental frequency, harmonic, and overtunes. Now we'll discuss like fundamental frequency, harmonics, overtunes, and resulting timbre. What is fundamental frequency? The lowest of any vibrating object is called the fundamental frequency. The fundamental frequency provides the sound with its strongest audible pitch reference. It is predominant frequency in any complex waveform. A sine wave is the simplest of all waveforms and contains only a single fundamental frequency and no harmonics, overtunes, or partials. Virtually all musical sounds have waves that are infinitely more complex than a sine wave. It is the addition of harmonics and overtunes to a wave that makes it possible to distinguish between different sounds and instruments, the timbre harmonics. The harmonic is one of the ascending series of sonic components that sound above the audible fundamental frequency. The higher frequency harmonics that sounds above the fundamental makes up the harmonic spectrum of the sound. Harmonics can be difficult to pursue distinctly as single components, nevertheless they are there. Harmonics have a lower amplitude than the fundamental frequency. Harmonics are integer multiples of the fundamental frequencies. Harmonics are the integer multiples of fundamental frequencies, like 2 multiplied, 3 multiplied, like. For example, if the fundamental frequency is suppose 50 Hz, also known as the first harmonic, then the second harmonics will be 100 Hz. That is 2 into 50 is 100 Hz. Third harmonics is 150. That means 50 into 3 and so on. Here, look at that. These are fundamental harmonics. This is second harmonics. Look here. This is the first and this second. Third harmonics is here 1, 2, and 3. Like it's continuous. What is overtunes? Overtunes are frequencies of a waveform that are higher than but not directly related to the fundamental frequency. It's an overtune. Two tones produced by different instruments might have the same fundamental frequency and thus the same pitch. Example, a C tone, C note, but sound very different because of the presence of different amounts of harmonics and overtunes. It is presence of harmonics and overtunes within the sound wave that helps to produce the sound unique sound. The timbre describes those characteristics of sound which allow the ear to distinguish sounds that have the same fundamental pitch. Timbre have same fundamental pitch. It is due to the timbre that we can distinguish one instrument from another. For example, a piano played at C3 sounds then different to a guitar plucked at C3. That means both are same C3 and C3 but it different sounds. Now we'll discuss about resonance. Objects, mechanical system and charged particles tend to vibrate to a specific frequency. We call this frequency the resonant frequency or the natural frequency. When a light or a sound wave strikes at an object that is already vibrating at some particular frequency, and if that frequency happens to match the resonant frequency of the object it is hitting, then you will get what's called resonance. That means at a point, natural frequency and artificial induced frequency become same. That happens resonance. Resonance occurs when the matching vibration of another object increases the amplitude of an object oscillations. Suppose you are creating a particular sound frequencies, that is you are creating a sound with particular frequency. Suppose it match the natural frequency of the wine glass. So by using sound only without touching this mechanically, we can break this glass. That means what? It's overtunes. Means both natural frequency and created frequency match. Then its resonance happens. Due to that resonance, the glass break. Resonance in physics is defined as follows. A phenomenon in which an external force or vibrating system forces another system around it to vibrate with greater amplitude at a specified frequency of operation. The concept of resonance would be harder to comprehend without examples. So let's explore the concept of resonance further in the context of some examples. Here, musical instruments. Whenever a person hits, strikes, strums, drums, or tweaks any musical instruments, the instrument is set into oscillation or vibration at the natural frequency of vibration of the instrument. A unique standing wave pattern defines each frequency of vibration as a specific instrument. These natural frequencies of a musical instruments are known widely as the harmonics of the specified instruments. Suppose a second interconnected objects or instruments vibrate or oscillates at that specified frequency. In that case, a first object can be forced to vibrate at a frequency higher than its natural harmonic frequencies. This phenomenon is known as resonance. That means one object vibrating or oscillating at the natural frequency of another object forces of other objects to vibrate at a frequency higher than its natural frequency. Swing, another example. The swing moves forward and backward when pushed. If a series of regular pushes are given to the swing, its motion can be built. The person pushing the swing has its synchronized with swing's time, which results in the swing's motion having increased amplitude to reach higher. Once the swing reaches its natural oscillation of frequency, a gentle push helps maintain its amplitude due to resonance. But if the push given is irregular, the swing will hardly vibrate, and this out of synchronous motion will never lead to resonance, and the swing will not go higher. Next example, bridge. Group of soldiers marching on the bridge are often asked to break their steps because their rhythmic matching can set extreme vibration at the bridge's natural frequency. The bridge can break apart if the synchronized footsteps resonate with the natural frequency. Natural frequency on the bridge, then it may collapse the bridge also. One of the example of the above is the Tacoma Bridge collapse, where the frequency of the air meshed with the frequency of the bridge, which then led to its destruction. How to calculate resonant frequencies? Resonant frequency of the natural is the natural frequency where a medium vibrates at the highest amplitude. Resonant frequency is usually denoted as F0. Resonance is witnessed in object in equilibrium with acting forces and could keep vibrating for a long time under the perfect condition. To find the resonant frequency of a single continuous wave, we use the normal formula V equal to F lambda, where V is the wave velocity and lambda is the distance of the wavelength. From that, we can find F equal to V over lambda. Different types of resonance. There are many types of resonance and something here. Mechanical resonance. Mechanical resonance can be defined as the tendency of a mechanical system to respond a greater amplitude. Greater amplitude when the frequency of its oscillations matches the system's natural frequency of vibration, its resonance frequency or resonant frequency, than it does at other frequencies. That means for some natural frequencies and created artificial frequencies, it matches, that mechanical resonance happen. The resonant frequency of a spring is calculated using the given formula F0 equal to 1 over 2 pi into root of k by m, where m is the mass of the spring, k is the spring constant. Acoustic resonance. Acoustic resonance is a phenomenon in which an acoustic system amplifies sound waves whose frequency matches one of its own natural frequency of vibration. Acoustic resonance is an important consideration for instrument builders, as most acoustic instruments, such as the length of tube in a flute, the string and body of the violin, and the shape of the drum membrane, use resonators. Acoustic resonance is also important for hearing. Acoustic must be correct position and correct frequencies, then only you can hear easily. Otherwise, it's more hard to hear. Electrical resonance. In a circuit, when the inductive resonance and the capacitive reactance are equal in magnitude, electrical resonance occurs. That means in a circuit, when inductive resistance L and the capacitive reactance C are equal in magnitude, electrical resonance occurs. The resonant frequency in LC circuit, inductance and capacitance circuit, is given by the formula omega equal to 1 by root of LC, that is equal to pi f, where F is the frequency of the resonance, L is the inductance and C is the capacitance. These are some explanation regarding resonance as well as resonant frequencies. Then we have done about fundamental and harmonic frequencies. We have done. Please subscribe our YouTube channel.